Hello, everyone. I just wanted to go over a few things to help you with the lab activity for this week, so let's get into it. So here I have this pencil, and I want to know what the length of this pencil is going to be. And I have this ruler here that's measured in centimeters. So here we have half a centimeter, 1 centimeter, 1.5, and so on. And I want to measure what this length is going to be. So we look here, we can kind of estimate that maybe it's like 4.8 centimeters or so. But then what's the accuracy in that measurement? Well, in this class, we're going to use the accuracy of the tool. So if we look here at the ruler, the distance between tick marks is going to be a half of a centimeter. So therefore, we're going to have this 4.8 that we mentioned earlier, plus or minus zero point 0.5 centimeters. Now, there are other conventions that are out there that will tell you what this number could be, but in this class, we're just going to use the accuracy of the tool to keep things kind of simple. Well, let's say we want to know this more accurately. So here I've got a new ruler here. Here you see that the distance between tick marks here is 0.1 centimeters. So we look here, we kind of estimate, it looks like it's maybe closer to 4.9 centimeters. And because the accuracy of our tool is 0.1 centimeters, that's the distance between tick marks, we get 4.9 plus or minus 0.1 centimeters. Well, what if you wanted to know exactly how long the pencil's going to be, like perfectly and exactly? Well, that turns out to be impossible. Let's say you zoom in really close to the end of this pencil here. Because the pencil's at room temperature, you can see those atoms are going to be vibrating kind of back and forth. Well, how can you measure the length when the kind of length is kind of shifting around? But you may be thinking back to chemistry where, oh, well, let's cool the pencil down to 0 Kelvin, where there's no vibrations there. Well, we can also zoom in. Well, we're trying to measure the outer shell of the electron there. Well, Heisenberg uncertainty principle states that we can't know the velocity and position at the same time. So there's just no way. There's no way to do it. That just happens to be the reality of the universe we live in. So every single measurement must have an uncertainty associated with it. It's impossible to know exactly the length of something or the time of something. In this class, I'm going to be very specific when I want you to record and use the uncertainty of your measured values, or when I'm just asking you to use that first measured value in some kind of calculation. For instance, in some of our lab reports, I'm going to have you do some graphical analysis. In those graphs, we're just going to use that measured value, just the first one, and we get the slope and the y-intercept and things from that. There is a way to use this uncertainty in graphical analysis, but we're not going to be doing that in this class. Just as a reminder, this is the slide from the previous video that I made. If you having some issues with this, please go back and watch that video, but I wanted to mention it because you're going to be using these calculations in the lab this week. Here's another example that I want to go over with you, and let's say we want to know what the width of this hallway is going to be, but all we have is one ruler. So we think, okay, well, let's measure the width of one tile, and then multiply that by how many tiles there are. So we see there's 8 tiles all the way across. So we can take that measured value and multiply it by 8 in order to get the full width of the hallway. So let's say that the width of one tile is 13.8 plus or minus 0.1 centimeters. Well, we can multiply that by 8, and let's see what that gets us. So D, which is the width of a tile, is going to be that value I just mentioned, and length is going to be 8 times that. Well, the uncertainty will follow that exact same calculation. So the length is going to be 8 times this 13.8, and the plus or minus 8 times the uncertainty in that width, which is 0.1. So we arrive at 110.4 plus or minus 0.8 centimeters. So you see that our final width calculation has a larger uncertainty than the width of one tile. That's because we're kind of using that tile multiple times, which is going to increase the uncertainty of our final measured value. Well, let's say we want to go the other direction. Let's say we have some measuring tape and we want to know what the width of one tile is going to be. So we can measure the full width of the hallway. Let's say it's 109.9 plus or minus 0.1 centimeters. I want to know the width of one tile. Well, I can just take that full length and divide by 8, and we'll follow that same calculation. So we take the full length divided by 8 plus or minus the uncertainty in that full length divided by 8. And that's going to give us 13.737 plus or minus 0.013 centimeters. If you look at this, the uncertainty in the width of our tile is much smaller than our tool, which is 0.1 centimeters. And that's because in order for this length to be within this same range of values, the distance or the width of a tile can't shift by that much, because if it shifts by more than this, then the uncertainty of our final measurement will be larger than what we measured it to be. Well, I hope this helps. Go ahead and get started on your activity for this week.